The first property that we have already proved is that the Cantor distribution is continuous. That is, if we take any random variable x having Cantor distribution, then for any fixed number in R, probability that x takes that value a is 0. And why is that true? We know that a distribution being continuous is equivalent to its CDF being continuous. Now let f denote the CDF of Cantor distribution. Then you have already seen that this f is the uniform limit of certain CDFs Fn. While each of these Fn's, as we have seen in the last two videos, are nothing but distribution functions of certain uniform distributions. So these Fn's correspond to density, so these are all continuous functions, and it's the uniform limit of continuous functions, hence f must be continuous. In fact, we used this argument when we showed that this is a CDF. We wanted to show that it is right continuous, but we showed that it actually is continuous. So as a byproduct, we get Cantor distribution is continuous. The next property that we want to mention is that the Cantor distribution does not admit density. To prove this, we shall quickly recall one technique by which we can prove that a distribution does not admit density. Suppose fx is some CDF. It doesn't have to be anything to do with Cantor distribution yet. I am just stating a result. I want to check if it admits a density or not. Then what I can do is I can define a potential candidate for a density as little fx, which is derivative of fx whenever the derivative exists. Otherwise, I set it equal to 0. I claim that this is the best candidate for being a density, which means if this function is not a density function, then no other density function can work here. If this fx is not a density, that is non-negative function integrating up to 1, then if it is not a density, then fx cannot admit a density. So if it has a density, this has got to be the one. Now let's come back to our Cantor distribution. Recall how we had created the Cantor distribution. We had started with 0, 1 and then taken the uniform distribution over it. The CDF of the uniform distribution over 0, 1 was like this. Then we removed the central open 1/3. As a result, the distribution function flattened out in the middle. In the next step, we remove 1/3 here and 1/3 here. Now the part that was already removed will never be restored. As a result, in all the subsequent things, the flat part will remain the flat part. So after I have removed these two intervals, the new CDF will look like this zigzag line. Observe that this flat region is still there and it will continue to be there in all the subsequent CDFs because I will never remove this gap. Similarly, once this gap is created, this gap will stay there. So the flat regions, once there is a flat part, it always remains a flat part, and as a result, when you take the limit, even in the limit, which is the Cantor distribution function, that will also have the flat part. So the CDF of Cantor distribution will have a flat part here, flat parts here, and all the little flat things will be flat in F. And as a result, for all x not in the Cantor set, that is all the things that are removed, all these open intervals, f dash x will be equal to 0 because they will be all the flat regions. Now observe that at each step, these flat regions are growing and growing and growing. And the very first step, what was the total size of the gaps? It was 0. There was no gap. After one step, the size of the gap was 1/3. After the next step, it is 1/3 that you already had, plus out of the remaining 2/3, I have removed 1/3. And in this way, the total length of C complement will turn out to be 1. So what is length of C? That will be equal to just 0. If you consider it as length, the length will be just 0. So what can I say about the derivative of f dash x? So what is the derivative of f? That is 0 over a set of length 1. Now the entire thing is already of length 1. So only in those points which are in the Cantor set, whose total length is 0, you can possibly have something else. As a result, you can see that your best candidate for density function becomes fx is equal to 0 for all these points, and it can possibly be non-zero only over a set whose length is 0. So when I integrate, what I do over a set of length 0 simply does not matter. For example, if I take a function and I integrate, I get something, and if I just change it over a single point, then the integral does not change. If I change it over a countable set, the integral does not change. In particular, if I change the function over only a set of length equal to 0, then the integral will not change. So I see that fx behaves just same as if had it been 0 everywhere. And if it is 0 everywhere, what is the total integral of this fx? Total integral of this fx will also be 0. So this fx cannot be a density, because a density must have total integral equal to 1. So we see the best possible candidate for the density fails to be a density, which means the Cantor distribution does not admit a density at all. Now that we have seen that the Cantor distribution is pretty weird in the sense that it does not allow PMF, it does not have a density, then how do we really work with it? And even its CDF is given as limit of something, so how do we deal with it? For example, if x has Cantor distribution and I ask you to find expected value of x or variance of x, what do you do? Well, the first question is that do they even exist? Well, they must exist. That is trivial in the sense that x is Cantor, which means it lies between 0 to 1. It can never take values outside 0 to 1. So it's a non-negative random variable, it's a bounded random variable, and every bounded random variable has finite expectation. So this exists, this must also exist, because here we deal with expected value of x squared. That's also bounded, so all the moments etc. exist. So existence is not a problem, but the question is how do you show that, how to find this thing. Now for this one it is not very difficult to guess once you remember that Cantor distribution can be thought of as uniform distribution over the Cantor set, and the way the Cantor set was obtained is a perfectly symmetric way, right? So whatever you are doing on this side, you are also doing on that side. So if x is Cantor, it is not difficult to say that 1 minus x, flipping thing around, will also be Cantor, because all the intermediate fn's, they also remain invariant under this transformation. So expected value of this should equal expected value of that, and that should immediately imply that it must be sitting right in the middle, so it should be half. But such a trick is difficult to work with when you are using x square, x cubes and things like that. Now in the next semester you will learn a technique by which you can actually relate the expectations computed from fn, which are of course nice densities. I mean CDF based on densities, so you can find out expectations based on these things and relate that to expectation of x. Basically, the the expectation that you will compute from this, take the limit, and they will give you expectations or the corresponding moments for x. But that will require certain results about convergence of random variables. So that's not part of the syllabus. I just wanted to mention that existence is not a problem, and for expected value of x, you can easily guess that it should be half. This exercise about trying to have an intuitive feel about the Cantor distribution as uniform distribution over the Cantor set. So I am going to ask you a true or false question. I start with two closed intervals inside 0, 1 such that their lengths are the same. My question is this statement true? Probability that x lies in AB is same as the probability that x lies in CD. Is this statement true or false?